So we're on topic 6, correlation. And this corresponds to the first part of chapter 10 in your book. I know we've skipped some chapters, and we're not going to do all this chapter. We're actually splitting this chapter up into 2, to correlation and regression, next week, because I'm going to go into a bit more detail than your book does on this. But everything you need to know will be covered in this presentation and in our SPSS instructional videos and examples. All right, so correlation just means a relationship or an association. The correlation coefficient is a type of descriptive statistic that summarizes the relationship between two variables, okay, two certain kind of variables. So an important thing here is that correlation is not the same as causation. Just because there's a relationship between two variables, or correlation in this case, does not mean that one causes the other, okay? We frequently talk about one variable that we put on the x-axis in a graph as the predictor variable, and the other variable that we put on the y-axis as the criterion. But this doesn't mean that we have any evidence of causality. So when we're talking about this, just think relationship, association. So we'll be dealing with two correlation coefficients, okay? These are calculated values that describe the relationship between two variables, okay? Two variables means bivariate. Bi is two, variate, variable, okay? Both have to be of quantitative data. We're going to talk about Pearson's correlation coefficient. We'll be focusing on that one, and Spearman's correlation coefficient, also called rho or R sub S. Pearson is just lowercase r. Both are italicized. Remember, we talked about how Latin letters are used to summarize samples, right? Statistics, and they are italicized. Okay, correlation assumes a linear relationship or non-linear relationship between the two variables. So what does this mean? Okay, as the score in X increases, the scores in Y tend to change in only one direction. Okay, either they both go up together, in which case it's a positive linear relationship, or as one goes up, the other one goes down. That will be a negative relationship, an inverse relationship. We'll also be talking about the regression line. We're going to go into more detail about that next topic, but this is also called the line of best fit, and it passes through the center of a scatter plot between these two variables in such a way that the difference between the predicted scores in Y from X and actual scores is the least. And we'll talk more about that, so don't worry about it now. So a one-to-one relationship or perfectly consistent relationship is just when changes in Y are exactly corresponding to changes in X in a predictable way. So here we have two variables, one that I made, right? On the x-axis, we have fiction. This was just the number of authors people recognized. And on the y-axis, we have a variable I created with compute variable. Right? Remember that from our first chapter? Second chapter, second topic. I just added 1 to each value in fiction, so we get a perfect one-to-one relationship here, right? Here's an example of a strong positive linear relationship, right? On the x-axis, we have the number of fantasy authors people recognized, and on the y-axis, the number of science fiction authors people recognized in a recognition test. And we can see that the more fantasy authors people recognized, okay, that's here. As fantasy goes up, so does science fiction. The more fantasy, the more science fiction people recognized, right? So this is a strong positive linear relationship. This line here is the line of best fit, okay, straight line that best fits the data. And we'll talk more about that next week, next topic, I should say. Here's an example of a weak negative relationship. You can see here that as scores on the x-axis increase, scores on the y-axis go down, right? The x-axis is modal possibility. That's the number of futuristic things people thought would someday be possible. And the y-axis is just discussed sensitivity. how people react to disgusting things. And the higher scores mean that they're more sensitive to and feel more disgust at certain disgusting things, right? Okay. So anyway, this is a negative relationship, but it's a not very strong one. This slope is gradual, right? So a change in X just has a very small change in Y. And there's the regression line. And finally, we have what is basically no relationship. When there is a flat line, when a change in X tells you absolutely nothing about what happens in Y, you end up with a flat line, and this is no correlation, no relationship. In this example, we have a big 5-factor of extroversion on the X-axis and attitudes towards helmet use in equestrians or horse riders on the Y-axis. And we can tell that they're pretty much independent. People's degree of extroversion has no relationship to their attitudes towards wearing a helmet. We can see that flat regression line there. Okay, these are all scatter plots, right? We talked about that in topic 2. Okay, so the correlation coefficient tells us the strength and direction of a relationship. The strength of relationship is just the extent to which a value of Y is consistently paired with one and only one value of X. So when we saw the one-to-one relationship, every value of X corresponded to one and only one value of Y. With a strong relationship, a strong positive relationship, as we saw, every value of X was corresponded to a limited number of Y values. And when there's no relationship, there's a lot of Y values for every value of X, such that it's just a flat line, right? So the strength of the relationship is indicated by the absolute value of the correlation coefficient, okay? So correlation coefficients go anywhere from -1 to 1, and the closer the absolute value of the coefficient is, the stronger the relationship. So, for example, 0.70 is stronger than 0.5, right? But -0.70 is also stronger than 0.5, okay? So it's the absolute value, right? The sign of the correlation coefficient just tells you whether it's positive or negative. So a positive sign, a positive correlation just means as X increases, so does Y, right? And a negative correlation just means as X increases, Y decreases, right? So the kind of questions you might think about are these. So what happens to Y as X changes, such as, does greater physical health mean more mental agility? Actually, this is true. Does higher high school GPA mean better performance in college? Yes, it's generally a good predictor, but not the best. The one example we saw, do people who read science fiction also read fantasy? We saw that, yes, there's a strong positive correlation between number of fantasy authors people recognize and number of science fiction authors they recognize. Is age related to moral identity? Do people who exercise more, so they say, tend to weigh less, and so forth, right? So there are problems, right? I talked about how correlation assumes a linear relationship. So we can see at the bottom of this slide, not a few examples of nonlinear relationships. See this curvilinear one. So at the beginning, as X increases, Y decreases, right? But then towards the end, it's a U-shaped function. As X increases, so does Y, right? Same thing, very similar happening here, right? Another big issue that we haven't talked about yet is restriction of range. Okay, when the range between the lowest and highest scores on one or both variables is limited, the correlation coefficient is going to be weaker or smaller than it would be if the range were not restricted. And we'll have an example of that later. So let's look at first an example of a nonlinear relationship, not appropriate for correlation. Okay, so HIV risk in years in education. We can see that it's pretty low in early years. People are young, okay? Then it gets higher in the teen years and lower again as people get a little bit older towards their 20s, right? Actually, these aren't maybe years of education. So 20s would be 13, 15. So right in 20s and 30s, they're the highest, and then it gets lower later, right? See what would, let's have a look at this. So for example, if we drew a straight line, a line of best fit, we could see that would tell us nothing about all those people with between 13 and 17 years of education, right? So people who have gone to college, some college through a 4-year degree, and the 17, 19, 21 are people who have a graduate degree, and they once again have less HIV risk. Okay. If we fit it with a curved line, it tells us a lot more, but this is not a correlation coefficient. You can do this with statistics, but not at this level. All right, so let's walk through an example. For example, we can say, what is the relationship between moral identity and aggression, right? We can guess that the more people report a greater sense of moral identity, the less aggression they're going to report as well. We can guess that, but we don't know. So far, what we can do, what we learned to do is how to get descriptive statistics, right? So we see the statistics here. We can see in this table, we can see aggression right here, moral identity. We can get their means, right? This is from the explore function, right? No, this is from frequencies, actually, look, frequencies. We can get the median, the mode, which we can only get in frequencies, the range, all those measures of central tendency and dispersion that we talked about the last couple of topics are right here, okay? We can also make histograms, right? We can see that it looks like moral identity has a bit of a negative skew, right? Right? We can do all that so far. We also know how to add a scatter plot to it, right? You guys have learned how to do this, and we can see this is a negative relationship, right? As scores on moral identity increase, scores on aggression decrease. Now, here I want to call your attention to the restriction of range issue. So here, these were both self-report measures. And as you can expect, people generally don't want to report being very aggressive. So we don't really have any high scores in aggression. At the same time, people tend to exaggerate how moral they are. So most people on the moral identity scale, which the values, it actually ranges from 1 to 6. There's no values less than, this is a 6-point scale, right? And we can see the mean's probably pretty high. And there's no values less than about 2.75. So we have restriction of range in both. People tend to exaggerate how moral they are and underreport how aggressive they are. Think if we didn't have a restriction of range and had a whole bunch of scores up here, we would probably have a much stronger relationship. So remember I said how restriction of range will make a relationship weaker or appear weaker than it really is in the population, okay? So far we can do that. We can also look at the pairs of scores. We can see moral identity and we can see aggression. That doesn't tell us much. So what about their correlation? Now, I'm going to show you a little later how to run a correlation analysis in SPSS. But for now, let's just look at this. This is their correlation, -0.298. And it says Pearson correlation, and we are going to learn about that in a minute. So Pearson's correlation, this is used for continuous data to scale or interval ratio variables such as self-report, moral aggression, and identity works for that. So Carl Pearson created this, okay? The Pearson's correlation coefficient is used to estimate the relationship between two interval ratio variables. It can also be used for dichotomous or two category variables, but we're going to focus on interval ratio variables here. Carl Pearson is an important statistician, or one of the biggest names in the history of statistics, okay? He was very much interested in the study of heredity and genetics. We talked about before, a lot of early statisticians were interested in frequently plant genetics, right? But he also had some less appealing traits as far as eugenics, right? So let's look at the formula for Pearson's correlation coefficient. As I said, it is denoted with a lowercase italicized r, okay? It's the covariance of x and y divided by the standard deviation of x times the standard deviation of y. So the covariance is just this right here. It's the sum of the deviations of x multiplied by the deviations of y, Okay, so remember PEMDAS. First, we multiply the deviations of X and times the deviation of Y, then we sum them all up. And we'll walk through a demonstration in a minute. Divided by N minus 1, okay, degrees of freedom. Remember the standard deviation is just the sum of the squared deviations right here, sum of squares. We'll talk about that later. We'll refer it to that way, divided by the degrees of freedom. And then you take the square root, right? So let's walk through an example, even though I probably won't make you calculate this. I'm going to stop this recording and we'll continue with a